Hello, we have been discussing techniques of integration, and this video is going to center on the major technique of integration called the substitution rule, or in other words, U substitution. Recall that the fundamental theorem of calculus established the inverse relationship between differentiation and integration. And so if you recall some techniques of differentiation, we have product rules, we have the chain rule, and whatnot. And the substitution rule is essentially undoing the chain rule. So in the beginning of this worksheet that you see before here, recall that the chain rule here, the derivative of a composition of functions, is the derivative of the outside evaluated at the inside, and then times the derivative of the inside. So I'm going to scroll forward before coming back to these examples, and just the substitution rule in general is that if we make a U substitution, so we're going to introduce a new variable because we recognize a composition of functions inside our integrand. So if our integral of f of x dx, if this function is a composition of functions, you might want to consider the substitution rule. So we want to look at grouping symbols. Remember what our grouping symbols are: square roots. If we have the square root of a function and underneath, then we would have a composition of functions. If we have something like e to the 5x plus 2, then that would be e to the quantity 5x plus 2, and that would be a composition of functions. If we have sine of x squared, that would be a composition of functions of sine x and the x squared function. So here, look at the substitution rule. If u is equal to g of x, and it's a differentiable function whose range is an interval and f is continuous on I, then our integral of f of g of x times g prime of x dx is equal to f of u du. So here I've just already outlined the proof here. If I just go ahead and let u equal to g of x, then I'm going to take its derivative, or take its differential. Then du is g prime of x dx. So if I just make those two substitutions into my original integral here, then I would substitute g of x with u, and I would substitute g prime of x dx with du. And it transforms our function into another function strictly in one variable, and we can then consider direct methods or possibly another technique of integration down the line if it might be more complicated. Good. So when do we want to use this property? It's really, we want to look for composition of functions within our f of x dx, and we want to go inside our grouping symbols, inside that composition of functions, and we want to make a mental derivative inside and see if at least the variable part of that derivative is on the outside of those grouping symbols. So now I'm going to go back to the front and just practice the techniques of substitution here. So I see in this first example, what is my composition of functions? I see cosine of a function. So I'm going to go inside, and I'm going to let my u substitution be x squared. I'm then going to take my differential du, and I get 2x dx. And I recognize that my entire du is on the outside of my composition. So I am very happy about that, and I know that if I just make my u substitution, that is going to transform my integral into something that I can integrate directly using the basic table of integrals. So in making that substitution, I would get cosine, and I would put in u, and I would have du on the outside. And just making that, then what function has derivative equal to cosine? Sine has derivative equal to cosine. This is an indefinite integral, so you don't want to forget the plus c. But because we start with an integral in x, we want to end with a function in x. So we want to back substitute. And that back substitution is going to be x squared. And that was a very basic one. And now I want to move forward to c, which is another basic one. I see here another composition of functions. And so I want to go inside and consider that to be my u substitution. And I want to say that this is u equal to 2x. Then du is equal to 2 dx. Now I have the variable part of my derivative, but I don't see the 2 in my integral. But I can multiply by 2 and then divide by 2, and that's the same as multiplying by 1. And if I just multiply by 1, I'm not going to change the value of the overall integral. So that's what I want to do. If I need a 2, I'm going to multiply by 2, and then I'm going to divide by 2 on the outside. So then I can extend my shaded here, and I can see that my 2 dx is going to be my du, and then I can transform my integral, and I still have my 1/2. I still have my cosine, but now I can use my u on the inside, and then my 2 dx becomes my du. Notice that I did not replace the 1/2, and I needed that. I can give an option or an optional way of playing with this that some other calculus teachers use as a way of demonstrating your u substitution. So now I have 1/2 times cosine u du. What's the integral of cosine u? What function has derivative equal to cosine u? Sine has that. So this is going to equal 1/2 sine u plus c. Because I started with a function in x, I want to end with a function in x. So I want to back substitute for my value of u. And my value of u here is 2x. And then don't forget the plus c. Same u substitution. This is just an alternate way that other people use to use u substitution. They would still use u equal to 2x. They would still take our derivative du dx, or they would still do du equal to 2 dx, but then they would solve for dx. So if they solve for dx, then they would get du over 2. And then if I took my integral of cosine 2x dx, I want to make a substitution for 2x, and I also want to make a substitution for dx, and I would get the integral of cosine, and my u would be 2x, and my du, or my dx would be du over 2, and you would be, oh, excuse me, this is supposed to be a u. I'd still get the same exact integral. I would still have 1/2 cosine u du, and I can continue. So that is another way that you can solve your substitution, or solve your integrals, or calculate your integrals using u substitution. So we can extend that. This one, part B, is very similar to that, so I'm going to move on to this one, and you might not see right away what it might be, but remember, we're looking for grouping symbols, or we're kind of looking for composition of functions. And I still see a composition of functions here if I remember that something from the basic table of integrals I have 1 over u du is equal to the ln of u plus c. So if I'm ever faced with a function that is 1 over or even 2 over, it doesn't matter what number's in the numerator, but if I have a constant over a linear function, something that is to the degree 1, I can remember having that basic table, and I might be able to consider U substitution. So don't forget that with a fraction, the numerator is entirely in parentheses and the denominator is entirely in parentheses. And I can see here, so we can extend this to other U substitutions as well. But I'm going to go inside, and I'm going to say U equal to 2t minus 1. I'm going to say du here is 2 dt. I notice that the dt, the variable part of my integral, is there, and I know that U substitution is going to work, but I do need a 2. So if I multiply by 2, I'm going to divide by 2. And now I'm going to make my U substitution, and I will transform my integral into 1/2 times the integral of 1 over, and I have u du because the 2 extends in there. Good. Now I can integrate directly, and I end up with 1/2 ln of absolute value of u plus c. I want to end in t because I started in t, so this is going to be the ln of 2t minus 1 plus c. And you can, of course, use your log rules if you wanted to say that this was equal to ln of the square root of 2t minus 1 plus c. That would be fine as well. Okay. All right. So let's do some more definitions. So here we've got, let's look at item C, because I think that you can probably handle part A, and I think that you can probably handle tangent as well, because it's very similar to the cosine. But let's take a look at example C here and recognize where is the grouping symbol, or where is that component of composition of functions. And I see a square here. So I'm going to go inside, and I'm going to say let u here equal 1 plus the square root of t, which does equal 1 plus t to the 1/2. And I'm going to say then du is going to equal 0 plus 1/2 t to the minus 1/2 dt. And if I simplify there, I do end up with 1/2 times 1 over root t dt, using my exponent rules for the t to the minus 1/2. T to the 1/2 is square root of t, and if it's a negative, I can move it to the denominator. So I do see that I have my 1 over dt. I have dt over 1 over the square root of t, but I need the 1/2. So I'm going to multiply by 1/2, and then divide by 1/2, and division by 1/2 is multiplication by 2. So now I'm going to, this extends my shaded, and this whole region here is my du part. So if I transform my integral, I have not changed the 2 because that's not part of it, or it's still part of the transformation, but I can see that this is going to be 1 over u squared, and then the shaded region is going to be du. Good. And we know using algebraic manipulations and then the basic table using the power rule, we can integrate. So we move forward and say that this is equal to 2 times u to the negative 2 du. You want to avoid calling that the ln u squared. Don't do that. Avoid that. It's just 1 over u. And then if I integrate here, u to the minus 2 plus 1 is minus 1. And then I divide by minus 1. And then I add plus c. And in simplifying that, 2 divided by negative 1 is going to be negative 2. U to the minus 1 can go down to the denominator. And that would be u to the first power, which is just u. And then I can back substitute. And when I back substitute, I move and make sure that I have my correct substitution, and my correct substitution is 1 plus the square root of t. So I would have negative 2 over 1 plus the square root of t plus c here. It is fine in a Calculus 1 or a Calculus 2 course to keep radicals in your denominator. You don't have to go overboard and over-rationalize your expressions, just to keep that in mind. All right, this one's a little bit tricky. I do want to, sometimes your success in doing U substitution is to recognize some patterns. I do think it is beneficial if you take the time to try to memorize the first 20 items on a basic integral table. And here I'm going to point out one integral table, and that is the integral of du over a squared plus u squared is going to be 1 over a times the inverse tangent of u over a plus c. Good. And I see here I've got a w to the 4th power, and I have a w dw in the numerator. So I'm going to look to first transform this to have some form of a composition of functions. So I see that this is w over 2 squared plus w squared squared dw. And in looking at this grouping symbol here, I'm going to let u equal w squared. And so my du, oh, that's kind of bizarre. My du is going to be 2w dw. And I have the variable part, so substitution is going to work. When you don't have the correct variable part, if you cannot transform your integral to be completely in u, in other words, another w is left over or another x is left over, then you have to be creative with your u substitution in order to completely transform your integral. And as we get further on in our techniques of integration, you will see ways that you can expand your substitution skill set. But here with this straight, direct U substitution, you want to ensure that whatever U substitution you make, when you make the derivative, at least the variable part of your derivative has to appear in your integrand, and you have to be able to transform your integral completely into U in order to consider integrating. So I do see the w dw, and I have w dw here, so I just need a 2, so I'm going to multiply by 2, and then I'm going to divide by 2, and now I'm going to transform my integral into 1/2 times the integral, and this 2 expands to the du, that is my du here. And I would have du over 2 squared plus u squared, right? And that helps me with my direct methods, and I'm going to employ that here. And this is going to equal, and I still have my 1/2. And I do see that my a is going to equal 2. So in transforming or evaluating this integral, I get 1 over 2 times the inverse tangent of u over 2 plus c. And in simplifying, I end up with 1/4 inverse tangent, and then I want to back substitute, and my back substitution would be w squared over 2 plus c. Good. All right. Next up, if you're given definite integrals, we have, instead of giving the proof here, just to shorten this, I might give a proof during our lecture period. We have two options in order to calculate a definite integral if we're going to use U substitution. Now, don't forget that if you have an integral with respect to x, then your limits of integration are going to be x equal to a and x equal to b. And those are your ranges to use for the fundamental theorem of calculus part 2 when we get to the f of b minus f of a, right? If you transform to u, then if you don't, you have two options to calculate your integral. You can make a U substitution. You can perform the integration and then back substitute for x and then perform the fundamental theorem of calculus. Or you can make a U substitution, change the limits of integration to be in u, and then take the calculate the integral with respect to u, but then you don't back substitute, and you can perform the fundamental theorem of calculus on u. So remember, if we're going to let u here, so I guess I could just do the proof. If we're going to let u here equal g of x, then du is going to be g prime of x dx. And we do see that the integral of f of g of x times g prime of x dx equal to f of u du. So we can say when x is equal to a, then u is equal to g of x. No. Then u of a is going to be g of a. And when x is equal to b, then u of b is going to be g of b. And so we do have here that u is equal to g of a, and u is equal to g of b. Good. So as I mentioned, there are two processes. So to calculate f of x dx from a to b, or f of g of x dx, from a to b, you can, one, use U substitution to evaluate the integral. You can back substitute for x. And then step 3, you can have that big f of g of x from a to b, and you can do the f of g of b minus the f of g of a, right? Or you can, to calculate your integral from a to b, you can, one, use, take your U substitution, u equal to g of x, and your du equal to g prime of x dx. Step 2 would be change your limits of integration to be in terms of u, and then you would integrate with respect to u, And then you would have your f of u, and you would have from u equal to g of a to u equal to g of b. In other words, you do not back substitute, and you would still get f of g of b minus f of g of a. I tend to like the second method if it's a straight U substitution, because there's no getting out of evaluating U at A and U at B, and I like to calculate those things separately instead of doing the fundamental theorem of calculus at the same time. So let's do an example. All right, so here we have evaluate the definite integral. Don't be alarmed if this looks a little strange, but I'm going to recognize that I've got a factor of 2, and I'm just going to move that out. So I'm just going to clean up a little bit, and I'm going to say that this is equal to 2 times 0 to 1 of e to the t plus 1 times the square root of e to the t plus t dt. I just factored out the 2 from that first product and then put that 2 as a constant outside of my integral because I'm allowed to do that. So I see a grouping symbol, and my grouping symbol here is the square root. So I'm going to go inside, and I'm going to let u equal e to the t plus t. And then I see that du here, the derivative of e to the t is e to the t. The derivative of t is 1. And then we have our differential dt. I see that on the outside of my grouping symbol that I have the variable part, so substitution is going to work. When you can't remove all of the t's, then substitution breaks down, and we're going to learn to use different methods of integration if that happens, or another more creative substitution method. So in making here, I'm going to change my limits of integration just to show you. So when t is equal to 0, then u is equal to e to the 0 plus 0, and e to the 0 is 1, and 1 plus 0 is 1. When t is equal to 1, then we have u is equal to e to the first power plus 1, which is just e plus 1. Good. So all I'm doing is taking my limits of integration. This is t and this is t, right? That's t equal to 0 and t equal to 1, and I'm just using the new definition of my variable u and just making a substitution and finding my new limits of integration. So then when I transform my integral, I end up with 2 times the integral, and now I'm going to use u equal to 1 to u equal to e plus 1, and I have my square root, and what's underneath my radical is just u, and then on the outside I have du. Good. And this is we can use the power rule by using algebra manipulations, and so I would end up with 2 times the integral from 1 to e plus 1 of u to the 1/2 du, and that's going to give me 2. If I add 1 to 1/2, I get 1.5, and 1.5 is 3/2, and I'm going to divide by 3/2. That's going to give me 2/3 times 2, so that's going to give me 4/3. Division by a fraction is multiplication by the reciprocal, and I have u to the 3/2. I'm not going to back substitute because I've already changed my limits of integration, and I'm going to go from 1 to e plus 1. So in using my f of e plus 1, take away my f of 1, I end up with 4/3 e plus 1 to the 3/2, take away 4/3 1 to the 3/2, and that's just going to give me 4/3 e plus 1 to the 3/2, take away 1. And that's my answer there. Good. One more, and then and practicing changing of limits of integration so that we get used to that. So I see here that I see a natural U substitution because I know that mentally the derivative of ln of x is equal to 1 over x. So I'm going to put a little parentheses in there. I'm going to clean up and just put the 5 on the outside. And I have from 1 to e of the ln of x over x dx. And I'm going to use u equal to the ln of x. Then du is 1 over x dx. And I see that my 1 over x dx is there. So substitution is going to work. I'm going to change my limits of integration when x is equal to 1, u is equal to the ln of 1, and that's equal to 0. When x is equal to e, u is equal to the ln of e, and that is equal to 1. And don't forget that we're using these guys. X is equal to 1 and x is equal to e because we're integrating with respect to x. So now I've changed my limits of integration, so I don't need to back substitute, and I'm going to transform. This is going to be 5 equal to times the integral, and now my first u is going to be 0, and my second u, my upper limit of integration, is going to be 1, and now I just have u du, right? And that's an easy integral to evaluate, and I get 5 times u squared over 2, evaluated from u equal to 0 to u equal to 1. I don't back substitute because I've changed my limits of integration. If I did not change my limits of integration, I would need to back substitute and then use my limits of integration with x. Okay, so when you use f of b minus f of a, those need to be in the same variables as your integral evaluation. So this is going to be 5/2 times 1 squared minus 0 squared, and that's just going to give me 5/2. Good. I hope that is helpful. I will answer other questions in class. Take care. Peace, health.